Hi there, in this lesson we're looking at inequalities within one triangle and really looking at the sides and the angles and how those different things relate to one another as it's contained in one triangle. Alright, so the first thing we're going to look at is the comparison property of inequality. And really this is super obvious, or should be super obvious, in that if I have A equals two things added together, and one of those things is bigger than 0, in other words I'm not dealing with any negatives here, then A, the sum of those two things, has to be bigger than that other guy. Alright, so if I have A equals B plus C and C is not negative, then A has to be bigger than B. Alright, and that makes sense because I need two smaller things in order to add up to a larger thing. So the thing that's being added to has to be bigger than the two pieces being added to get it. Alright? In terms of using that, the first thing we're going to do is look at another corollary here. This is the corollary to the triangle exterior angle theorem. Remember, the triangle exterior angle theorem says that the exterior angle of a triangle equals the sum of the remote interiors. And so this is kind of related to that, and we're going to use that theorem to prove this guy. But if we're given triangle ABC and we're told that angle 1 is an exterior angle, I want to prove that the measure of angle 1 is greater than the measure of angle 3. I also want to prove that the measure of angle 1 is greater than the measure of angle 4. So I'm going to set this up in terms of my statements and reasons. I'm going to do a two-column proof. And I always start with what's given. So first of all, that I have a triangle and that angle 1 is exterior. And that's given. And so then the next thing I can do here is I can use that triangle exterior angle theorem to say that I know that the measure of angle 1 equals the measure of angle 3 plus the measure of angle 4. And from here, I'm going to use that property, that comparison property that we just talked about, but I can't quite use it yet. And I'm just going to describe this. Exterior angle equals sum . Okay. I can't quite use that yet because I have to establish, when we look at this property up here, the thing that's established is that this guy is greater than 0. So I have to establish that, and that's really easy to do. In fact, the reason that part of my given is that I have a triangle is because that allows me to say that the measure of angle 3 is greater than 0 and the measure of angle 4 is greater than 0 because I have triangle ABC. Alright, if either one of those was not greater than 0, I would not have a triangle because I wouldn't have one of those angles. Alright, so now from here, I can immediately say that the measure of angle 1 is greater than the measure of angle 3. I can also say that the measure of angle 1 is greater than the measure of angle 4 because of that comparison property. Okay, which basically says, hey, those two added together equals this thing, so that thing is bigger than each of those two pieces that we're adding. Okay, and that might seem obvious, and again, it should be, but that's what this theorem says. All right, or this corollary to the theorem says. All right, so if we have an exterior angle, then its measurement is greater than each of the remote interior angles. Okay. In addition to that, and we can use this to prove these, but I've kind of summarized a couple theorems here that we're going to use within the next couple problems. And these theorems basically relate the angles and the sides of the triangles. We really have these as separate theorems, but I'm just going to summarize them, and we're just going to use them collectively, which is fine for our purposes. But basically it tells us that there's a relationship between the length of a side and the measure of the opposite angle. Okay, or the measure of the angle and the measure of the opposite side. So when we look at this, really it's essentially telling us that the largest angle is across from the largest side and the largest side across from the largest angle, which means the smallest side is across from the smallest angle. And so there's a relationship that exists in terms of these lengths and these angle measurements that kind of correspond in terms of size, all right? So the largest angle is always across from the largest side. The smallest angle is always across from the smallest side. The angle that's the middle measurement is always across from the side that has the middle measurement, okay? So when we kind of put this into action a little bit, if we look at something like this, it just says to list the sides or angles from least to greatest. So in the first one, we're going to list the sides from least to greatest because we're given the angles. And so when I look at the sides of this thing, I can immediately see that the smallest side is going to be side B because it's across from the smallest angle, okay? And so there's a relationship between the size of the angle and the size of the side opposite that angle. So in this one, the smallest side would be side B. The next smallest side, again, I look at the next smallest angle is this guy, which means the next smallest side is side A. So B is less than A, but then each of those is less than what must be the longest side because this is the largest angle, so this must be the longest side. And so now we've listed these from least to greatest. I can tell right away, based on these theorems, that the smallest side is B, the largest side is C, and A is somewhere in between the two. Okay? I can do the same thing with the angles. When I look at the angle measurements here, again, I can tell which angle is the smallest angle because it has to be across from the smallest side. So the smallest side is 17. The smallest angle must be angle 2. All right? And that measurement has to be less than, well, the next smallest angle, the side marked as 20, the angle opposite that is the angle 1, so the measure of angle 1 comes next. And then the largest angle that's in here has to be angle 3 because it's across from the largest side. Okay? And again, we've taken, it's really two theorems here that we've kind of summarized a little bit. But basically, the size of the side and the angle opposite that side have this unique relationship where, in terms of inequalities with the rest of the angles and sides in the triangle. Okay? And so the next thing we're going to look at, the triangle inequality theorem. The triangle inequality theorem really should be obvious as we start to construct triangles, but it basically says that if I have two sides of the triangle, they have to add up to be bigger than the third side. Because if they don't, I wouldn't be able to use those to construct the triangle. All right, and so given this triangle, I want to prove that the measurement of xy plus the measurement of yz has to be bigger than the third side. And so in order to do this one, it's really tough because when we look at what's given, it's basically nothing. There's almost no information that's given to us here. So typically when that happens, we have to construct something. And in this particular example, it's not obvious what needs to be constructed. I'm basically going to construct a point out here in space to continue this line. And I'm going to call it point P. And basically, I'm going to construct that to make sure that point P is the same distance from y as y and z are from one another. Okay? So out here, I'm going to construct another piece of this triangle. So I extend this line out to point P, making sure that that point is equidistant from y as z is from y. Okay? So I'm making sure those are the same. And I'm going to finish off that triangle. So now I'm really working with a couple different triangles here. I've got the really big triangle, which is PXZ, and I have a smaller triangle, PYZ, and then I have my original triangle, which is XYZ. All right? And so in terms of the given here, I can state that I have triangle XYZ. I'll also state that PY, that measurement is equal to YZ, and that's because I constructed it that way. And so in terms of my reasoning, I'm just going to say given / constructed. Because really the constructions are become part of our given as we draw those out. So I'm just going to include those in one step. And now I'm going to go from here. I'm also going to label some of these angles to make things a little bit easier for myself. I'll call this angle 1, angle 2, angle 3. And I could label other angles, but I believe those are the ones I'm going to need. And so the first thing that should be obvious to us is that angle 1 is equal to angle 2, or their measurements are equal, rather. We could say that they're congruent to one another, but we'll just skip that step and just say the measure of angle 1 is equal to the measure of angle 2. And we know that because those are the base angles of an isosceles triangle. And so then from there, I can start using some of these theorems that I just had in terms of the relationships. So like I might look at something like this and say, okay, well, now I can immediately say that when I look at this, the angle P, measure of angle PZX, all right, has to be greater than the measure of angle 2. I can also say the same thing about the measure of angle 3. I missed my angle symbol over here. So I can say the measurement of PZX is greater than the measure of angle 3. And that's because of my comparison property. When I think about angle addition here, I know that those two added together equals the whole thing, so the whole thing must be greater than each of those pieces. So that's my comparison property. And then from here, the theorems that we got after that, really when I look at something like this, I can also say here that when I look at this guy, since I know that that larger angle is bigger than angle 2 and angle 3, I can really say the same thing about angle 1. Measure of angle PZX is greater than the measure of angle 1. Because I know that angles 1 and 2 are the same, and that's really just substitution. I can also say then, when I look at this very closely, if I know that angle 1 is smaller than angle PZX, I can make an assumption about the opposite sides to those. So when I look at this, I know then from this guy, PZX, the side opposite that would be side PX. And that has to be greater than the side that's opposite angle 1, which is side XZ. And then from here, oh, sorry, I need to justify that. That comes from the relationships in terms of the lengths of the sides. So I'm just going to say relationship of angles and sides in a triangle. And that was the summarized theorems that we just looked at. I could do the same thing with other pieces of this thing. I could also say that, you know, PX is, XY is, PX is greater than something like XY using that measure of angle 3. I don't know if I necessarily need that at this point. But really, what it then comes down to is when I look at something like this guy, I look at that line on the top, PX, and I should realize that PX is actually equal to XY plus YP, and that's my segment addition postulate. And then from there I can do a little bit of substitution. I know right away that PX PX equals this guy, so I can plug that in for PX in the previous step, that XY plus YP is greater than XZ. Again, I'm just plugging that in right here. And then from there, it's really just one more step of substitution when I look at it. That's substitution. And then from here, I know that XP and YZ are the same thing. That was all the way back in my given. So I can replace that that YP with YZ. And so what I end up with is that XY plus YZ has to be greater than XZ. And that's the thing that I wanted to prove, and that was just by another bit of substitution. Okay, so as I said earlier, I did not end up needing this guy, I just needed the other one. Okay? And in fact, I really didn't need this guy at all either. If we wanted to simplify this thing a little bit. All right, and you know, it's okay to include those things. You never know exactly what you're going to need as you continue through the proof, but now I can see that, yeah, those two sides have to add up to be more than the third side. And really, when you think about it, you know, if I have a triangle if you just think about this logically, if I come back up here a little bit, if I have a triangle that's this long, if this side and this side don't add up to that third side, what happens is they're not long enough to connect. See? As I get closer and closer to this thing, they're not long enough to connect. If they're the same length, I can't connect them in terms of a triangle. They have to be just a little bit bigger in order to make this thing a triangle, okay? Or those sides are going to never be able to connect. And so all this says is the sum of the lengths of any two sides has to be greater than the third side, all right? So when we're looking at triangles, if I take any two sides, they have to add up to more than the third side. And that's it, okay? If we don't have that situation, then we essentially don't have a triangle because there's no way that those pieces can connect, all right? So the two sides, whichever two sides you choose, have to add up to more than that third side. For example, if I look at these guys, it says, determine if the triangle with the given side lengths is possible. And so really all we do is we just add them up and we say, okay, let's add the first two together. It gives me a 10, which is greater than the 8, so that works. If I add the second two together, it gives me a 15, which is greater than the 3, so that works. If I add up the only two that I haven't done, the 8 and the 3, that gives me an 11, and that's greater than the 7, which works. And so since each of these equalities works, I can safely say that yes, these could be the sides of a triangle. If I look at the next set, right away when I see the first two, if I add the first two together, I get 15, and I want to look at this and say, okay, 15 has to be greater than the third side, which is 15. Well, right away, that's not true. That doesn't work. So there's no way that these could be the side lengths of a triangle. All right, and even though, despite the fact that it might work with the others, like when I add the second two together, I get 25 is greater than 5, and that works. And then I add the last two together, and I get 20 is greater than 10, and that works. All of these need to work, okay? And if I choose any two sides, it has to be greater than the third side. So even though two of them work, the third one doesn't. So no, it's impossible to have these as lengths of the sides of a triangle, okay? And then the last one, it says if a triangle has two sides measuring 5 feet and 8 feet, what are the possible values of the third side? And so when you think about this, let's call the third side x. So I'll say I've got 5, 8, and I've got x. There's a couple inequalities that happen here. First of all, when I add the first two together, that gives me a 13, so 13 has to be greater than x. That's the first thing I notice. The next thing I have would be like, if I did the 5 plus the x, that has to be greater than the 8. Okay? And then the last thing I would have is that if I did 8 plus the x, it has to be greater than the 5. All right, and so what I have is I have a couple inequalities, and I want to condense these a little bit, so I'm going to solve two of these and just see what kind of x values it leaves me with. So here it says that x has to be greater than 3. Here, when I subtract this guy, it says that x has to be greater than a negative 3. And so when I look at this, obviously the negative 3 doesn't make any sense, but it's still redundant because if I have one where x has to be greater than a 3, I can't have one where it's negative 2 or 1 or 0. So it kind of eliminates this last one. So I basically have these two inequalities, which I can combine into one. I have to have x that's greater than 3, and I have to have an x that's less than 13. So in other words, x has to be between 3 and 13. So x has to be greater than 3 and less than 13. So I come up with this range of values, and I list it as a compound inequality. Okay?